These series of videos are based on the Good Science textbook, years 9 and 10, specifically chapter 2 on motion. So chapter 2 in a nutshell is about forces, how we can quantify motion, so how we can describe motion around us in terms of equations, formulas, numbers. So the study of forces, it didn't come out of vacuum, it didn't come out of nowhere, it come out of years and years of work. If you go back to the ancient Greeks were familiar with what a force was, although not in the modern sense that we now understand. Forces were things that kept things moving, let's say. And then came along people like Galileo, the famous Italian thinker, who studied motion in more detail, and then Isaac Newton came along. And chapter 2 is mainly based around people like Sir Isaac Newton. So Isaac Newton was an English polymath. Polymath means he specialized in a lot of different things. Poly means many, right? He was like a physicist, mathematician, astronomer, alchemist, theologian, and so on and so forth. And he came up with a series of scientific physical principles. Okay, these were basic foundational statements that describe the natural world, describe what's happening around us. And these are based on scientific evidence that's well supported and it's accepted by the majority of the scientific community. So it wasn't that Isaac Newton just started writing down all these ideas. He had to develop these ideas and make sure they were right over the years. So forces, let's talk forces. What's a force? A force is, and I'm grinding my teeth over this because it's not really right, but anyway, loosely speaking, a force is a push, pull, or twist. And we use forces every single day. It's necessary for our existence. Opening a door, carrying your books from your desk to your locker, opening a jar, the list goes on. Now, so Isaac Newton found that there's a relationship between force and the mass of an object. If you really think about it intuitively, it's really logical, right? The heavier an object is, the more force you need to apply to it, right? 2 textbooks stacked on top of each other will weigh more than, let's say, a piece of paper. You need more force to lift it up. So there's no surprises there. Force is proportional. It's related to mass somehow. Now, how is it related to mass? It's related to mass in terms of acceleration A. This is one of the most basic formulas in physics. F stands for force. M stands for mass. A stands for acceleration. It's a very simple relationship. Force is measured in newtons, in honor of Newton. Capital N for newtons. So Newton, capital N. The more newtons, the more force. Mass is measured in kilograms. In physics, the SI units are internationally recognized units. Doesn't matter if you're in South Africa or Switzerland, you use the same units. So kilograms, small k, small g. Acceleration is measured in meters per second squared. I'll explain that in a moment. But for now, that's the formula. So why is this important? Well, Newton redefined force. It's not just a push or a pull. It's something that causes acceleration. F causes acceleration. If I kick a ball on the ground, it'll accelerate. It'll move rapidly. This formula F equals ma is known as Newton's second law of motion. So he came up with 3 laws of motion. I'll talk about the others later. But it's known as Newton's second law of motion. For any object with mass m, if you apply a force to it, it'll accelerate. So if you apply, so this is loosely speaking, if you apply a force to a mass m, it'll accelerate. So physics is about thinking conceptually. Think in terms of pictures. That's why a lot of students struggle with physics, because they can't really think in terms of pictures. Try and think in terms of pictures. Think outside the textbook. Here's a ball of mass m. I kick it with force F. It'll accelerate with acceleration A. Acceleration is a measure of how quickly an object's speed or direction of motion changes. Let me define acceleration mathematically. Acceleration A is equal to the change in velocity over the change in time. Delta, this is the Greek symbol delta, capital delta. Lowercase delta is this, curly d, but anyway, capital delta, it means change in So you can have delta capital T, that's change in temperature, delta lowercase p, change in delta uppercase P, that's change in pressure, and so on and so forth. But the top bit means, so change in velocity means your final velocity minus your initial velocity. Suppose I've got a ball moving between points A and B. At point B, where it stops, it's got a final velocity v sub f. F is final. And at point A, where it starts moving, it's got a velocity v sub I. So delta V is final velocity minus initial velocity. And delta T is just the final time minus the initial time. That's how you calculate acceleration mathematically. So final minus initial. Sometimes in physics, they'll write it like this: final velocity V, initial velocity U. Okay, it's the same thing. Now, why is acceleration? Why does it have units of meters per second squared? Because think of the numerator. This thing, velocity, has units. Both of these things are velocity, meters per second. And this in the denominator has units of second. So you get meters per second squared. So acceleration is how quickly something changes its speed or direction. Okay, for example, if I put my foot down on the accelerator of a car, here's my foot, and I give the car more gas, it'll accelerate more. I'm applying a force to the pedal, the car will accelerate. I'm giving it more force to move faster. Just a note, if an object's just sitting there on the ground, is stationary, in other words, its acceleration is 0. Or if it's moving at constant speed, if a car's moving at 50 k's per hour, its acceleration is 0. Acceleration, you have to have a change in speed. In other words, if the car's just sitting there, its velocity is 0 initially, right? However, if I give it some gas, it'll start to accelerate, let's say, I don't know, 50 k's an hour. You have a change in velocity here. Velocity is changing over time, let's say 10 seconds. That's acceleration. So that's acceleration. Back to the formula, mass is, just a note, mass is the amount of stuff, the amount of matter in an object. So the more matter in an object, the heavier it is, the more mass it has. Suppose I have a box here, 2 boxes of same dimensions. If I have, let's say, 10 marbles, or let's say 5 marbles versus 2 marbles, the box with 5 marbles is heavier. It's got more mass than the box with 2 marbles. I think that's quite logical there. But that, in a nutshell, that's F equals ma, quite simply. I'll show you some examples, some things they can ask you in an exam, let's say. Suppose object has mass 10 kilos and accelerates at a rate of 2 meters per second squared. What's the force? Physics is all about having a recipe, steps, step by step. 2 things, you can either panic and break down here, or you can just follow these steps, just like when you're baking a cake, right? You have to have steps. You can't expect to have a cake made out of nowhere. Step 1, you always write down what you're given. We're given mass, and we're given acceleration. M is 10 kilograms. Acceleration A is 2 meters per second squared. We need, step 2, force. How do you work out force? How do we know how to relate? How do we relate mass and acceleration? It's just using F equals ma. Quite simply. 3, sub and solve. So sub in, so F is M is 10, A is 2. So 10 times 2, that's 20 newtons. That's how much force you need to move a mass of 10 kilograms to have it accelerating at 2 meters per second squared. I'll do another example. Calculate the acceleration of an object if a force of 20 newtons is applied for a 5 kilogram mass. Okay, step 1, given. What are we given? We're given force. So underline, I recommend you underline stuff, important stuff. F is 20 newtons. Acceleration, mass I should say, is 5 kilograms. Step 2, we need F equals ma. Step 3, we sub and solve. Now, your assumed knowledge here is basic algebra and arithmetic from basic maths. F is 20, M is 5, and A is unknown. How do you solve this thing? So 5 times something is 20. You can do this using your head, or you can do this using algebra. I'll use algebra. So to get the a by itself, you divide both sides by a. Whatever you do to one side of an equation, you have to do to the other side. The 5's cancel out, so you're left with a is 20 over 5, and that is 4. It's not just 4, it's 4 meters per second squared. Have to have units. And I'll do one more. This one more symbolic. Suppose I double the acceleration of an object of mass m. They like to ask this in an exam. What happens to the force? We need to convert this in terms of symbols. This is like a symbolic question. We need F equals ma. Start there. If you double the acceleration, that means if you multiply by 2, right? That's what double means. If you put 2 here, now it's preferable you put the 2 out here because this is one thing stuck together, m times a. If you double the acceleration, because this is a linear relationship, linear means when one thing increases, the other thing should increase or decrease, vice versa. If it's 2 times a, the force will also be 2, double. So force doubles as well. F equals ma. If a goes up by 2, F has to go up by 2. Okay, it's a linear relationship. If you plot F versus a, the slope, the gradient, so you get a straight line. The slope, the gradient, in other words, is m. You've got a constant slope here. It makes sense because the mass of an object is always constant. It's the same. Your mass doesn't change when you move. It stays the same. So that's why when you plot it, it's a straight line. It's a constant straight line because mass is a constant. If you increase F, you increase A. So if A is 2, F is 2. If A is 10, F is 10. So that's how you figure things like this out. You have to write the formula and recognize that this is linear, which means if one goes up, the other goes up as well. So that's Newton's second law of motion.